In this video, we're going to take a look at modeling real-life problems using recurrence relations.
So remember that a recurrence relation is really just for a sequence of values that expresses each value in the sequence in terms of one or more of the other previous terms. And when we talked about this before, we talked about the importance of the initial conditions, and those essentially give us the value of anything that occurs before the recurrence relation takes effect. So for instance, we have the number of bacteria in a colony doubles every hour. If the colony begins with 5 bacteria, how many will be present in n hours? So what we want to do is essentially just write this as a recurrence relation. So when I write it as a recurrence relation, I'm going to start with a sub 0, which means what are we starting with? When we begin, before the first hour passes, when I start at time 0, how many bacteria are there? And that is 5 bacteria. Now remember that it's going to double every hour. So a sub 1 would be 2 times 5, which is 10. And a sub 2 would be 2 times 10, which is 20. And really, I don't care about those values. What I'm looking for is how am I going to express this in terms of whatever happened before. So if I were to write my recurrence relation, I know that when I found A1, I was taking 2 times A0. And when I found A2, I was taking 2 times A1. And so my recurrence relation, my answer, would be that I start by saying that A0 will be 5, and then anything after that is going to be taking 2 times the previous value. So A sub n is 2 times A to the n, A of n minus 1, which means 1, whatever happened previously, whatever happened prior to that. And again, it's best to use n here instead of using a to the n plus 1. That can get a little bit confusing. So this would be my solution for writing it as a recurrence relation. So let's take a look at an example. We are looking at the same example we just looked at, but what I want to do is I want to write it as an explicit function instead. So this is the recurrence relation that we had come up with previously. Remember, it has 2 parts. That's the initial value and the recurrence relation. Now I want to find an explicit function, which means instead of relying each time on what value did I have before, which is what happens in a recurrence relation, I want to write it so that all I have to do is input n somewhere and find a solution. So let's take a look at the process I might go through in order to do that. Remember that A0 is 5. My first value is 5. A1, according to my recurrence relation, says take 2 times A0. And 2 times A0 would be 2 times 5. And I could write that as 10, but I'm just going to leave it as 2 times 5. A2 would be 2 times A1. And remember, A1 was 2 times 5. So I could really write that as 2 squared times 5. And then A3 would be 2 A2s. And that means 2 of all of this, so 2 times 2 times 5. Or 2 to the third times 5. So we can see what's happening here. This was really 2 to the 0 times 5. And this was 2 to the first times 5. And so if I keep going, I can say that the nth term, any term that I want, would be 2 to the n times 5. So I found it just by looking for the pattern. We call that basically an iterative sequence, so we're looking at each term and how it relates to the term before it. So now if I wanted to find A3, which I had previously found to be 2 to the third times 5, which would be 40. Instead of having to do that by finding that this was 10 and then taking it, I'm sorry, this was 20 and taking it times 2, and this was 10 and taking it times 2, and this was 5 and taking it times 2. Instead, I can just say, hey, if I want A3, that's going to be 2 to the third times 5, which is 40, and it's just a lot faster, especially if I'm looking for something like A200. Then I would definitely not want to have to find all of the 199 terms that happened before. Now let's take a look at how the Fibonacci sequence came about. So a young pair of opposite gender rabbits is placed on an island. The pair cannot breed until they are 2 months old. After they are 2 months old, each pair of rabbits produces another pair each month. And let's assume, scarily enough, that the rabbits never die. We're going to find a recurrence relation for the number of rabbits on the island after n months. Now, we've already talked about the recurrence relation for Fibonacci numbers, but this is how it came about. So let's take a look. The first month, we have my 2 rabbits, a male and a female. We have a pair, and they're too young to be breeding. The next month, month 2, they're now old enough to breed, but have not yet reproduced. So then month 3, these 2 guys create 2 brand new rabbits. So I've got a pair that is ready to breed and a pair of brand new little babies. The next month, these guys are still ready to breed. Their new little babies are a month old, so they're ready to breed for the next month. And then the green couple had another pair of babies. So my green couple stays green. These guys who were yellow now are old enough to breed. Both my green pairs have had a pair of babies, and these guys become ready to breed. So this is kind of the pattern that we're going through. So let's take a look at how we might put this into table form to maybe help us to make sense of what's going on. In the first month, I have 1 young pair. They're not able to reproduce yet. I don't have any reproducing pairs, so I have just a total of 1 pair of rabbits. In the next month, my young pair is old enough now to reproduce, but hasn't yet reproduced. So any active rabbits will be, of course, we're going to take that times, or get another pair out of them. So right now I still just have 1. Now my young pair has now moved over here. And because they've moved over there, they've had a baby. And so, well, a pair of babies, I guess we would say. And so in month 3, I have my active pair and my young pair is not old enough to breed yet. So now I have 2 total pairs of rabbits. In the next month, I still have my active pair, and my pair that was young before is now old enough to reproduce but has not yet reproduced. But my active pair has had another pair. So I have a total of 3 pairs of rabbits. Again, this time my active pair is still active. This pair of rabbits is now active as well, and they both reproduce a pair of rabbits. My non-reproducing pair is now ready to reproduce on the next try, and so right now I have 5 pairs of rabbits. Then again, following that same pattern, I've got my 2 active pairs plus my guy who's becoming active, my pair who's becoming active, and each of those pairs has a baby. In addition, I've got my 2 that were not ready to reproduce are now ready to reproduce, and so now I have 8. So here's sort of the way that this is set up, and before we look at it in terms of a recursive definition, I want to just point out to you that this value matches this value, and this value matches this value. And we can see that that's going to be helpful to us as we're moving forward. So what I'm looking for is, how am I going to write this so that it makes sense? Well, really what I'm looking at is I'm taking, to find 8, I'm taking the number of pairs that I had before, and then I'm also adding the 3 because those are going to be the couple that are old enough to reproduce. So what I'm looking at is, to find the value, I'm taking the value before that plus the value before that. So I'm taking f of n, or fn, equals the 2 terms before that. Now remember that it's only a recurrence relation or a recursive definition if it also includes the initial conditions. And of course the initial conditions are that in the first month I have 1 pair of rabbits, and in the second month I have 1 pair of rabbits. So this is the initial, and then from here this is where the recurrence relation takes effect. So now I could use that recurrence relation to determine, say, how many rabbits I'll have in month 10 or 20 or 100 or 1000. Let's take a look at the Tower of Hanoi question. And the Tower of Hanoi is basically a popular puzzle that asks you to take disks and move them from where they are located, we'll just call this 1, over to 2. And we want to move them to 2 so that they're in the same order that they are in now. However, I can only move 1 disk at a time, and I can only stack disks so that the larger one is on the bottom and the smaller one is on the top, which means I can't just move this guy and then move the next one and move the next one all over to 3 and then move them back. It's not going to work that way. So what I'm looking at here is to write this as a recurrence relation. So I'm not trying to find this explicitly yet. I just want to look at the recursive definition of how I would write this. So remember that a recursive definition starts with how many times would it take for, say, 1 disk. So for 1 disk, if I just had 1 guy, I would just have 1 move, because that 1 move would take the disk here and move it to tower 2, which is where I want it. This is where we want them to all end up. So great, there's my initial condition. Now I want to find what's the recursive definition. And remember that I'm not looking for a specific number. I'm just saying in terms of what? In terms of some value before. So what I know is that this set would be n minus 1 disks, because I start with n disks. And what I need to do is take these n minus 1 disks and move them over here to 3, so that I can get to this last disk to move it over to 2. And then I have to take all of those disks and move them back to 2. Now again, I'm not saying how many moves that will take. I'm just going to write this recursively. So my recursive part of the definition is saying, to find the number of total moves, I'm going to take 2 times the number of moves it would take to do n minus 1 disks, and then I'm going to add 1 so that I can get the bottom disk where I want it to go. So this is my recursive definition, and you might think, well, that's not super helpful, and it's not yet, because again, this doesn't help me unless I want to take the time to say, hey, if I do this with just 1 disk, then it's 1 move. And if I do this with 2 disks, then I have to move the smallest disk over to 3, so that's 1 move, and then the bottom disk to 2, so that's another move, and then the smallest disk back on top to 2, which is 3 total moves. And so if I wanted to keep this going for 3, for 4, for 5, and look for a pattern that way, I could, but instead I sort of went the opposite direction and said, this is how many it would take to move n minus 1 disks, and that's all I need for a recursive definition.
So again, that's not super helpful because what I really want more than anything is a closed form or explicit definition. And that's what we're going to do now. Now, I wrote it out ahead of time because I am prone to making mistakes when I'm trying to write things that are complicated and speak at the same time. So I wrote it out ahead of time so I wouldn't mess up what I'm writing, so I can just focus on not messing up what I'm saying. So this is the formula that we came up with previously. This was our recursive definition. To find the next value in the sequence, we take 2 times the value before it, and then we add 1. And if you'll notice, what I've done here is I've said, okay, well, what about this guy? Can I do anything with that? This is that iterative approach that we've used previously in this course. So if I wanted to know what is h of n minus 1, according to this definition, I would take 2 of h n minus 2 plus 1. And so notice I've just replaced that value for h n minus 1. And then I did that again for h n minus 2. I replaced it with 2 h n minus 3 plus 1. And the reason that I'm doing that is, of course, to try to find a pattern. So this is the pattern that I'm starting to develop, and I can see that I'm taking 2 to some value times the previous value. And then notice I've got some more going on over here. So this is the definition, or this is the pattern that I'm starting to see, is that I have 2 to the n minus 1 times h1 plus 2 to the n minus 2 plus 2 to the n minus 3 plus 2 to the n minus 4, all the way up until I get to the n minus 1, which would be 2 to the first, and then 2 to the n minus n, which is 2 to the 0, or 1. So I can see that that's the pattern that's happening. And notice now all I'm going to do is replace this h1 with the value for h1, which we determined in the other just a moment ago, that it was just one move to take one disk and move it to the proper position. So I've replaced h1 with 1. So now what I'm looking at is that I have 2 to some power, and that power is continually decreasing. Well, what I know about a series like that, or a sequence like that, is that it's a geometric sequence. That's this. And I'm just going to use the formula for a geometric sequence to simplify all of this. And so what I'm going to do is I'm going to say, I know that I have an a value and an r value in a geometric sequence. And the a value is some initial condition, which we already determined was 1. And the r value is that common ratio, or what it is that we do to get from 1 to the next. So to get from 1 to the next value, I would multiply by 2, because of course that's what's happening here. And to get from 1 to the next value, I would multiply by 2. And so that is my r, both here and here. And then I'm just doing some simplification. So I didn't really care about the 1, because when we multiply by 1, it's just 1. So on the numerator, I have 1 minus 2 to the n, and my denominator, 1 minus 2, is negative 1. And then, of course, I just simplified that by distributing the negative to the numerator. So I had a negative 1 and positive 2, and then I wrote it as 2 to the n minus 1. So this is actually my closed form expression for solving the Tower of Hanoi. So if I wanted to know how many moves does it take to move 5 disks, I would take 2 to the 5th and subtract 1. So 2 to the 5th is 32, minus 1 would be 31 total moves. Let's take a look now at a bit string question. We want to find the number of bit strings of length n that do not have 2 consecutive zeros. And there's an easy way to do this, which is just to find the answer. And then there's, of course, the harder way, which is to understand why the answer is the way it is. So I would challenge you to, be that second student that tries to understand why the value is the way it is, so that you can, apply that knowledge to other questions. We here are looking for length n bit strings that do not have 2 consecutive zeros, and if you'll notice, I've written out size 1, size 2, and size 3 already, but I haven't taken into account that I don't want 2 consecutive zeros. For size 1, both of my answers work because it's obviously size 1, so I can't have 2 consecutive zeros. For size 2, the only value that doesn't work is the double bit string of 0, 0. So there are 3 here. And then for size 3, I have to get rid of 3 of them. And so there are 5 total that don't have consecutive zeros. So the easy way out is to say, well, 2 plus 3 is 5, so maybe that works. And then you would find size 4. And if size 4 had 8 possibilities, then you would feel pretty confident in your abilities to say, just add the 2 values before. But let's make sure we understand or verify that that in fact works. So what I want to do is I'm going to write the 2 of size 1 that I have and the 3, oops, I'm going to do it this way, 1, 0, and 1, 1, and 0, 1. And I'm going to try to sort of match those up to what I have in size 3. So I have 0, 1, 0, this guy right here. I'm going to add a 1, 0 to the end of 0. And then I have 1, 0, and I'm going to add a 1 to that. 1, 0, 1. So I've used that one. And for 1, 1, I've got 1, 1, 1, 1, 1, 1. And for 0, 1, I have 0, 1, 1. And for the last one, I have 1, 1, 0. So my question is, do you notice any pattern with how I've done this? How did I go from size 1 to size 3 and from size 2 to size 3? Because that's sort of our conjecture, is that we would just add 2 plus 3, but why does that work? Well, let's take a look at the size 1s. For size 1, it looks like if it was size 1, I added a 1, 0 to the end of it. And if it was a size 2, I added a 1 to the end of it. Now, does that make sense? Could I continue that pattern? Well, it does make sense, because what I'm basically saying is if I have a total of n bit strings, if this guy is a 1, then it doesn't matter what the value is right before it. It could be a 0, because 0, 1 doesn't break any rules of having 2 zeros in a row, or it could be a 1, because having 2 1s in a row doesn't break any rules. So all of these values before my last value is n minus 1 values. So I'm taking that and then just adding a 1 to the end. And then for my other situation where I have 2 values, for my other situation where I have just the 1 value, if this guy is a 0, then this guy has to be a 1. So this would be n minus 2 values. And again, that adds up to n total values. So again, why is this going to work? Because what I'm saying is I'm taking all of the ones from 2 prior to that and just adding a 1, 0. And I'm taking all of the ones 1 prior to that and adding a 1, and that adds up to the total. So essentially what I'm saying is to find a sub n, let me switch colors here. To find a sub n, I'm going to just simply add a sub n minus 1 and a sub n minus 2. Now, is that what we said at the beginning when I said it was going to be the easy way out? It is, but now it makes sense to me because I'm saying I'm taking all of the size 1 values and I'm adding 1, 0, and all of the size 2's and adding 1, and I could continue that pattern throughout for the rest of our questions because it fits this guy right here. I'm either taking all of the n minus 1's and just adding a value, or the n minus 2's and adding the 2 values at the end. Up next, we're going to take a look at the principle of inclusion-exclusion.